Hey, hi guys. You may have heard that taking log of x or doing 1 over x can improve the fit of your regression model. This may be motivated by seeing a curve in the scatter plot of y versus x or in a residual plot of residuals versus the x's. But a problem with such scatter plots is that they are not designed to pick up partial relationships in multiple regression. Wouldn't it be good to supplement graphical methods by some estimation procedure to suggest a transform on the x's? Yes, it would, and today we're going to look at one such method, so let's get cracking. One of the assumptions of standard regression is that the relationship between y or transformed y is linear with x or transformed x. If we regress y on the x's when some of the x's enter in a transformed way, then the nice properties of least squares like the estimator being unbiased go out the window. Yep, so we want to fix this. We are interested in the case where the assumptions of the classical regression model are satisfied, except that the relationship between the y and the regressor is not linear, but can be made linear using a suitable transformation on the x. There are many approaches to modeling the functional form of the x's, and our interest today is on the box Tidwell transform here after BT. BT considers powers of x in a regression and looks like this. In the setup, BT is applicable for x's that are continuous and greater than 0. Other conditions to running BT are the usual assumptions of classical regression, namely the error term is normally distributed and homogeneity, or approximately so. Errors are assumed to be independent. As in the box-Cox transform, the powers denoted by lambda are unknown and are estimated along with the other parameters. The lambdas may be different for each x. If a power other than 1 is needed, it means the relationship between y and that x is non-linear, and we hope to straighten it out with the transform. Now you'll be glad to hear the popular log and reciprocal transformed x's are included in BT. A power of 0 is the log transform and a power of -1 is the reciprocal. So here's how we'd use BT. Step 1. Fit model and do residual analysis. If the residual plots for normality and constant variance are okay, then we don't need to transform y. If we did, it might mess up these two things. Look at the partial residual plots for each x, continuous ones only, remember. If a partial residual plot picks up on nonlinearity for any x's, we run BT on those x's. That is, we don't have to run BT on all x's just because some of them may need to be transformed. Step 2. We run BT. We can break this into 3 bits. To illustrate, suppose we have 4 x's and are interested in testing whether x1, x2, x3 need a transform. First, test whether any x's need a power transform. Add terms of the form x times log x to each of x1 to x3 like this. Then use the usual t-test to test for individual significance of each of the x times log x term. The null hypothesis is that the coefficient on x log x is not significant, which is the same as saying no power transform on x is needed. If more than one x log x term is non-significant, then you could use backward elimination, dropping the least significant one and fit again, and repeat until either none or all the remaining x log x terms are significant. Remember that the t-test is a one at a time test and not to be used like a partial f-test. Atkinson recommends running a partial f-test on all the x log x terms in the first run of BT. Second, have a look at the added variable plot of the terms x log x to see whether the decision to transform is due to any influential points. Third, refit or explore influential cases. If no influential cases, refit with transformed x, otherwise deal with the influential cases. Let's look at an example. Here we have data on occupational info collected from 102 people. The variables are y is prestige, a score of occupational prestige. The x's are years of education and income in dollars. So first we regress y on income and education. The residual plot looks fine, no signs of heterodiscacity, no outliers, QQ, normality plot seems fine. Here's the partial residual plot for income. There is a clear nonlinear pattern that looks like a log income. We'll try BT on income. The score statistic, which is the same as the t-stat, tests whether income needs a BT power transform. The null hypothesis is that no power transform is needed. The test value is -4.21 with a p-value of less than 0.01, so there's strong evidence to reject the null of no BT transform. The MLE for the power is 0.04. It's close to 0, and if you've watched my video on box-Cox transform, this corresponds to a log transform on x. Okay, so now we check the added variable plot for BT on income to check whether the suggested power transform is due to any influential values. This plot links up to the BT test. The slope of the line through the points is the coefficient on income times log income. A slope of 0 corresponds to not rejecting the null of no TD transform on income. You see there are a few points of high leverage to the right of the plot. If you imagine the plot without these few points, would the line be horizontal, i.e. is the reason the slope is not 0 due to a few unusual points? If you judge the answer to be no, go ahead with the transform on income and refit the model with income replaced by log income. On the other hand, if you think these points of high leverage is the reason why the line has non-zero slope, then investigate these isolated points. We'll accept the power transform is needed. Here is the partial residual plot for log income. You'll see it's fine now. Example 2. So manually getting t-test on x log x terms. So you're going to have to do this if your software you're using doesn't do BT. Going back to the prestige data to test the significance of income times log income, we regress prestige on income, education, and the income times log income term, and here's the output juxtaposed with the score stat using a package that does BT. You see that the results match as it should. What packages to BT? R does it through the car package. Stata, you need to download the program boxtid. SAS, download the macro. SPSS, at its current time, you do it manually. Does BT work on any type of non-linearity on X? It works on non-linearities of the type where X is raised to the power of a number. We've seen this covers the transform, log X, and 1 over X. X is less than 0. BT do not mention what to do for X with negative values. Using the idea in the box-Cox transformation, we could add a number to each observation to make all the x's, making them all greater than 0, which is the same as shifting the origin of x's. The units of the new x should be meaningful. Where do the x log x terms come from in the BT test? We do this using a first order Taylor series expansion on lambda around 1. What this means is that the closer the true lambda is to 1, the smaller the sum of the higher order terms in the Taylor series expansion, and so the better is the approximation. If true lambda is 1, then x does not need to be transformed. The rest of the details are here. Take your time and enjoy. What are partial residual plots and added variable plots? These are important plots that you might not have seen. Look out for them on my videos in YouTube. References. So I've used Montgomery before. It's good on the technical explanation of the BT algorithm. Fox is great. It's less technical, but very good on the explanation, and I used the prestige dataset from the book. Atkinson is another good reference. Okay guys, that's the end of the presentation and we can all relax now. Hope you've got some good stuff out of the video you can use. And how did you find my presentation? It's certainly different to classroom setting. Why do something like in a classroom when you are on YouTube?